Woodward Fieser Rule for calculating absorption maxima in dienes. Woodward Fieser Rule is a set of empirically derived rules which attempt to predict wavelength of absorption maxima, that is lambda max, in ultraviolet or visible region of a spectrum for a compound. Now this rule Woodward initiated and Fieser extended for theoretical calculation of absorption maxima in dienes. These rules are specifically for dienes. Now, absorption maxima is the wavelength at which substance shows maximum absorption. Here the rules are focusing on calculation of lambda max for dienes. The dienes should possess conjugated system, and longer the conjugation, greater is the wavelength of absorption. Now let us consider what are the different types of dienes. Very first type of diene is alicyclic diene. Now alicyclic diene is an open chain system. The best example is 1,3-butadiene. This is a open chain diene system with a conjugation. The main thing here to consider is conjugation should be there in a system. Then the second one is homoannular conjugated double bonds. Homoannular conjugated double bonds or homodienes are the conjugated double bonds present in a same ring. Now consider the two examples where the conjugation in a double bond and the double bonds are there in a same ring. Then the third one is heteroannular conjugated double bonds or heteroannular dienes are the conjugated double bonds which are not present in a same ring. Now let us consider the examples where the two double bonds are in conjugation but not in a same ring. Now the fourth one is exocyclic and endocyclic conjugated double bond. The very first thing is exocyclic double bond. These are the double bonds outside the ring structure, where the endocyclic double bonds are the double bonds inside the ring structure. Now consider figure 1 where we can clearly see the presence of exocyclic double bond and endocyclic double bond. Now let us consider the example 2 where there are two rings, ring A and ring B, containing double bonds in conjugation with each other. Now for ring B there is a exocyclic double bond, and also for ring B there is a endocyclic double bond. Now consider example 3 with two rings A and B attached to each other. Now the double bond are present in ring B. These two double bonds are exocyclic to ring A. Now here this ring A consists of two exocyclic double bond. Now consider example 4. Again with ring A and B attached with each other. The two rings consist of a double bonds in conjugation with each other, where the two double bonds are exocyclic double bonds to two different rings. That is, A ring also consists of a double bond and ring B also consists of a exocyclic double bond. Now consider example 5 where two rings are attached with a double bond, so they are having a exocyclic double bond. Now, Woodward Fieser formulated certain empirical rules for calculating lambda max in case of dienes. These rules consist of a certain fixed basic values, and the values of absorption maxima depends upon these values as well as the presence of chromophore oxochrome group in the form of alkyl substituent, number of double bonds and presence of other groups. For example, the number of alkyl substituent or ring residue on double bond. Then the second one is number of double bonds with extended conjugation, and the third one is presence of polar groups such as Cl, Br, Or, Sr. The next slide shows the table for lambda max. Now the three basic things in this table are butadiene system, then acyclic trine, homoannular and heteroannular conjugated diene with their specific lambda max. For butadiene type system, the lambda max is 217 millimicron as a basic unit. For acyclic, it is 245 millimicron. For homoannular, it is 253, and for heteroannular, it is 215 millimicron. Then the increment due to presence of each substituent are there, that is, if alkyl substituent or ring residue is there, then there is an increment of 5 millimicron. If exocyclic double bond is there, then the increment of 5 millimicron. If the double bond extending conjugation is present, then it gives increment of 30 millimicron. And if oxochrome groups are there, for example OR, it gives plus 6, SR then plus 30 millimicron. If Cl and Br are there, then each will give of 5 millimicron, and if Nr2 is there, then it will give plus 60 millimicron. Now presence of the COCH3 has no effect. Now let us solve some example on Woodward Fieser rule. Let us consider the example of 2,4-hexadiene. Now this is the structure of 2,4-hexadiene. Now in case of hexadiene, the basic unit is 2,1,3-hexadiene and value is 217 millimicron. And also this unit is attached with 2 alkyl substituent, and therefore the increment is of 10 millimicron, and uh, adding 217 plus 10 millimicron, the calculated value for lambda max is 227 millimicron for 2,4-hexadiene. Now let us have second example. In this example, we are having a ring attached with a butadiene unit. So initially we have to separate butadiene unit from entire structure. For that we have to give 2 cuts to a ring and also to separate 2 alkyl substituent to isolate butadiene unit. Now this butadiene unit is associated with 2 alkyl substituent and 2 ring residue. Now how we get this ring residue? When we cut the ring, in order to separate conjugation, each cut will yield 1 ring residue. So we are having 2 cuts to a ring in order to isolate conjugated structure, and therefore we are having 2 ring residues. Now this ring is attached to a double bond, which is again a increment due to presence of exocyclic double bond. Now here we are having a basic unit of butadiene with lambda max value of 217 millimicron, then alkyl substituent 2 with increment of 10, ring residue 2 again 10 increment, and a exocyclic double bond with increment of 5 millimicron, and therefore calculated value is 242 millimicron for this particular type of example. Now let us consider third example where the 2 benzene rings are attached with a single bond. Now in this case again we are having a 2 double bonds in 2 different rings. Now here the basic unit is heteroannular diene. In order to separate conjugated system, we have to give 4 cuts in a structure, and we are aware that each cut will yield 1 ring residue, so we will be getting 4 ring residues, and therefore basic unit heteroannular diene and 4 ring residue, so 215 plus 20 millimicron, we are getting 235 millimicron for this particular type of structure. Now let us have example 5. Here 2 rings are attached and the double bond is present in a same ring. Therefore basic unit is homoannular diene. To separate conjugated system, we have to make 3 cuts in a structure, and each cut will yield 1 ring residue, so 3 ring residue we are getting. If we mark these 2 rings as a ring A and ring B, then we observe that a ring B is having 1 exocyclic double bond. So we are having total value 273 millimicron. Now example 5 is a structure where 3 benzene rings are attached. Now here we are having 2 double bonds in a same ring as well as in 2 different rings. But the value of lambda max is higher for homoannular diene. Therefore, we will consider basic unit as a homoannular diene. To separate conjugated system, we have to give 5 cuts, and these 5 cuts will yield 5 different ring residues. So here we are having 5 ring residues with 5 cuts. Now if we consider for ring 1 the 2 double bonds as a conjugated system, then in ring 2 the 2 double bonds are the double bonds which are extending conjugation. That is, the double bond again present in a conjugation but are not a part of basic butadiene unit. Now, if we label them as a ring A and ring B, then the ring B is having one exocyclic double bond. So, in total, as we consider basic value of homoannular diene 253 millimicron, ring residue 5 ring residues, so 25 millimicron, then double bond extending conjugation present are 2, so 60 millimicron, and one exocyclic double bond, so 5 millimicron. So in total we are having 343 millimicron as a lambda max